Right now, the space between the stars sits at a temperature of negative 454 degrees Fahrenheit. That number has a name in physics, 2.7 Kelvin, and it represents something almost incomprehensible, the leftover warmth of the Big Bang itself. 13.8 billion years of cooling spread across a universe where 99% of everything that exists is dark and empty and cold beyond any ordinary reckoning. Most people, when they hear that number, feel satisfied. They came looking for an answer, and 2.7 Kelvin sounds like one. It sounds precise. It sounds final. But that confident answer is wrong. Not slightly wrong. Not wrong in some technical footnote that only physicists care about. Fundamentally wrong, in a way that changes what the question even means. If you enjoy journeys that completely reshape how you see the universe, do me a small favor and hit that like button and subscribe. It helps more than you know, and I genuinely appreciate every single one of you who supports this channel. Now, settle in and get yourself comfortable. Let's begin. Think about the cold you already know. Step outside on a January night somewhere like northern Minnesota, and the cold is not passive. It is immediate and aggressive. Within seconds, the skin on your face begins to sting. Within minutes, your fingers lose their fine motor control. Within an hour, without shelter, you are in genuine danger. That experience feels like cold attacking you, like the night itself is reaching in and pulling the warmth out of your body. And that feeling, as natural and as real as it is actually pointing you toward a deep misunderstanding. Because what you are experiencing in that Minnesota night is not cold as a force. It is heat leaving your body through a process called conduction, and the air around you is full of the molecules that make that process possible. This brings us to the crucial distinction that most people never learn. There are three ways heat moves through the universe. The first is conduction, which is direct contact, heat passing from one vibrating molecule to the next, like a chain of small collisions transferring energy along a surface. The second is convection, which is the movement of a fluid or a gas carrying heat from one place to another, the way a heated room gradually becomes warmer throughout as air circulates, or the way ocean currents carry thermal energy across entire hemispheres. The third is radiation, which is the emission of energy as electromagnetic waves. No matter touching anything, no molecules required at all. Every object in the universe with any temperature above absolute zero does this. It radiates energy outward simply by virtue of being warm. Now here is what changes everything. Conduction requires two objects to be in contact. Convection requires a medium, a gas, a liquid, something to carry the heat from place to place. Both of them require matter, and in deep space there is almost none. At sea level, the air filling the room you are sitting in right now contains approximately 25 billion molecules in every cubic centimeter. Every space roughly the size of the tip of your smallest finger. And that number is so large that it barely registers on first hearing. So take a moment with it. 25 billion. If you counted one molecule per second without stopping, not sleeping, not eating, just counting. It would take you roughly 800 billion years to finish counting the molecules in a volume of air the size of a sugar cube. The universe itself is only 13.8 billion years old. You would need to run that counting exercise 50 or 60 times, each one spanning the entire current age of the universe, before you reach the end of the molecules in a single sugar cube of ordinary air. That is the density of matter surrounding you right now, in the room where you are sitting, breathing, staying warm without thinking about it. In interstellar space, the vast regions between the stars that make up most of the volume of every galaxy, a cubic centimeter contains roughly one atom, not 1 billion, not 1,000, one, possibly less, depending on the region. The stage, as a way of thinking about it, is almost completely empty, and temperature, as a concept, is a story about that stage being full. It is a description of how fast molecules are moving, how often they are colliding, how vigorously the matter in a given space is transferring energy from one particle to the next. Cold is not a thing. Cold is the absence of a thing. It is the name we give to a low level of molecular motion, to the near stillness of matter that has surrendered most of its energy. And if there is almost no matter present at all, the story that temperature tells has almost no actors left to tell it with. Consider what this means for something as simple as a thermometer. A thermometer does not read the temperature of the space around it by detecting some property of emptiness itself. It reads the temperature of its own physical substance, the vibration of its own molecules, which changes when it gains or loses energy through contact with other matter, through conduction. Put a thermometer in a room, and the air molecules colliding against its surface transfer their energy into it, and the thermometer reads the temperature of that air. Put the same thermometer in a sealed vacuum container, and suddenly those collisions stop. There is nothing to conduct heat into or out of the glass and the fluid inside. The thermometer does not suddenly read 0. It reads whatever temperature it already was when the last molecule touched it, gradually drifting as it radiates energy away or absorbs radiation coming from elsewhere. A thermometer in deep space would not read the temperature of space. It would read its own temperature, slowly changing as it exchanged radiation with distant stars and the faint background glow of the universe, but never reading something as straightforward as the temperature of the emptiness surrounding it, because that emptiness does not have a temperature in any ordinary sense of the word. This is what begins to dissolve when you examine that number closely. 2.7. Kelvin is not the temperature of the emptiness between the stars, the way the temperature in your living room is the temperature of the air inside it. The concept, applied to a near-perfect vacuum, is reaching the edge of what it can meaningfully describe, and that leaves exactly one mechanism still operating: radiation. Heat moving not through matter, not through contact, not through the flow of a medium, but purely as waves of energy crossing the void. Of the 3 ways the universe moves heat around, that is the only one that survives in the spaces between the stars, which means if you were floating in that interstellar dark, your body's warmth would not be conducted away by air molecules slamming into you. It would leave you in a different way entirely, through a process that is quieter and slower, and in some ways far stranger than anything you have felt on a cold January night. Radiation, then, is the only remaining actor. And what radiation does in space, what it actually does to a physical object exposed to the void, is nothing like the simple, uniform freezing that most people carry as their working image of what space feels like. The intuition is understandable. You hear that space is cold, that the temperature between the stars hovers near absolute 0, and you picture something like a very large freezer, uniformly hostile, relentlessly draining heat from anything placed inside it. But that picture is wrong in a way that is not a minor correction. It is not a matter of adjusting the numbers. The entire character of the threat is different from what that image suggests. Space does not envelop you in cold the way a freezer does. It does not press a uniform chill against every surface of your body simultaneously. And it does something stranger, and in many ways more violent than that. It divides you. It splits the thermal experience of a single object into 2 completely opposite extremes. And it does this at the same moment, across the same body, with nothing in between. Consider an astronaut performing a spacewalk in low Earth orbit. The side of their suit facing the sun is struck by approximately 1,360 watts of solar energy for every square meter of surface area. That is not a negligible amount of heat. 1,360 watts is roughly comparable to a small space heater, and it is being pressed against every square meter of fabric facing the sun, continuously, without interruption. The result is that the sunlit face of an astronaut's suit can climb past 120 degrees Celsius, well above the boiling point of water, hot enough to cook food, hot enough that if you pressed your bare hand against a surface that temperature, you would sustain serious burns within seconds. Now turn that astronaut 90 degrees, or simply look at the opposite side of their body, the side resting in shadow, the side that faces not toward the sun, but away from it, toward the open darkness of space. That side receives almost no incoming radiation at all. It sits exposed to the void, slowly radiating away what little heat it has, with almost nothing arriving to replace what leaves. The shadow side of an astronaut's suit can drop below 100 degrees Celsius below zero. I'm pushing toward 170 degrees below zero as exposure continues. The gap between those two sides of that single body, the sunlit face and the shadowed face of one person floating in one place, spans something approaching 300 degrees Celsius. Not across a continent, not between two cities at opposite ends of the planet, but across the width of a human being. Across the distance you could reach with your own two arms. This is the first crack in the common understanding of space and temperature. The simple question, how cold is it out there, becomes unanswerable in any single number, because the answer depends entirely on which direction you are facing. And the two answers it gives you simultaneously are not just different, but separated by a thermal gulf larger than almost anything you will encounter in ordinary life. To feel how large that gulf actually is, consider the moon, which offers the same phenomenon stretched across an entire landscape. At the lunar equator, the surface temperature during the day climbs to 127 degrees Celsius, hotter than boiling water, hot enough that any pool of liquid water sitting there would be gone almost instantly. Then the sun sets, the 2-week lunar night begins, and without an atmosphere to hold any heat in place, the same patch of ground, the exact same square of rock and dust that was baking in the sun hours before, drops to 173 degrees Celsius below zero. Yes, the swing between those two conditions, experienced by a single location on the moon's surface as the lunar day turns to night and back again, is 300 degrees. Earth's harshest deserts, places like the Sahara or the Atacama, where temperature swings are considered extreme by any terrestrial standard, manage perhaps 50 to 60 degrees between their hottest afternoons and their coldest nights. The moon does 5 times that. It does it on the same ground, in the same place, simply from the presence and then the absence of direct sunlight, because there is no air, no ocean current, no atmospheric buffer of any kind to catch the energy as it arrives or slow its escape as it leaves. That is what the absence of a medium actually means in thermal terms. It is not just that space is cold. It is that space has no interest in moderation. Without a fluid medium surrounding you, without atmosphere, without ocean, without anything to absorb excess heat and spread it around, every thermal input arrives at full intensity and every thermal loss proceeds without resistance. The sun hits you and there is nothing to distribute what it delivers. You turn away from the sun and there is nothing to slow what radiates away. Space does not attack you with cold. It removes the buffer that would protect you from both extremes at once, and it leaves you alone with whatever radiation happens to be striking you in that particular direction at that particular moment. But all of that, the ferocity of the sun's output, the 300-degree swings, the thermal cliff between sunlight and shadow, all of that depends on proximity to a star, yet it requires a source, something burning close enough that its radiation still arrives with enough energy to matter, which raises a question that the numbers do not yet answer. What happens to an object that drifts beyond the reach of any star's light, out into the spaces between the furnaces, where almost no radiation is arriving at all? The question of what happens beyond any star's light is the right place to be heading, but before we arrive there, it is worth pausing on what the engineering of human survival in near-Earth space actually reveals about the thermal environment closer to home, because the solutions required are not simple, and their scale tells you something that the raw numbers alone do not. The International Space Station is the most thermally sophisticated human structure ever built. It carries 6 crew members at any given time, a population smaller than a single household on a suburban street, people who sleep in spaces roughly the size of a telephone booth, and work in modules not much larger than a school bus interior. And to keep those 6 people alive in the thermal sense, not comfortable, not particularly warm by household standards, simply alive, within a temperature range that does not kill them. The station requires a radiator array covering roughly 2,500 square feet. That is not the area of the station itself. That is not the solar panels, which are a separate structure with a separate purpose. That is specifically the radiators. Yes, so the components whose sole function is to reject heat, to take the thermal energy generated by the crew's bodies and their electronics and their life support systems and push it away into space as infrared radiation, because there is no other way to shed it. 2,500 square feet is larger than the floor area of most American homes. It is the size of a reasonably generous single-family house laid flat in orbit, doing nothing except trying to bleed heat into the vacuum so that 6 people do not cook in their own thermal output. Sit with that engineering reality for a moment. 6 human beings require that much infrastructure just to manage the thermal indifference of the vacuum around them. There is no atmosphere to carry the heat away. There is no ground to conduct it into. There is no fluid surrounding the station that absorbs excess warmth and redistributes it somewhere else. The only exit for any heat generated inside the station is radiation, and if the radiators are insufficient, if their area is too small, if they face the wrong direction, if they malfunction, the temperature inside rises with no natural check on it whatsoever. The station also carries electric heaters, not because space is uniformly cold, but because portions of the station that enter shadow and face away from the sun simultaneously can begin losing heat faster than the systems generate it. Both problems are real. Both can kill. The station must manage excess heat and insufficient heat, sometimes in different parts of its structure at the same time. Yet because the thermal environment it orbits within is not uniform and never stays still, that last part matters more than it might first appear. The International Space Station completes one full orbit of the Earth every 90 minutes. Every 90 minutes, it travels from full sunlight into shadow and back again, cycling through the complete range of its thermal environment 16 times in a single Earth day. When a shadow crosses the station, it does not arrive gradually the way a cloud's shadow slides across a field on a breezy afternoon. In orbit, where there is no atmosphere to scatter and soften incoming light, the transition from full solar illumination to complete darkness is nearly instantaneous. Yes, the station moves from roughly 1,300 watts of solar energy arriving at every square meter of its sunlit surface to essentially zero, across a boundary so sharp that mission controllers refer to entering eclipse as crossing a thermal cliff. The structure itself, the aluminum and steel and composite materials that form the station's skeleton, responds to that transition by beginning to shed the heat it absorbed in sunlight, radiating it outward into the blackness, and the temperature of exposed surfaces can drop by more than 100 degrees Celsius in the span of a few minutes. Then, 90 minutes later, the sun returns, and the same surfaces must absorb the sudden reintroduction of that full 1,300 watts, while the heating systems adjust in the opposite direction, 16 times a day, every day, without exception, for as long as the station flies. The thermal control system that manages all of this, the pumps and fluid loops and radiator panels and heaters and sensors and the software coordinating them, is not an afterthought added to make crew life comfortable. It is one of the foundational engineering challenges that had to be solved before human occupation of the station was even possible, and it required decades of development across multiple space programs to get right. The Russians and the Americans each brought different approaches to thermal management when the station was being assembled, and reconciling those approaches into a single coherent system was one of the more technically demanding aspects of the entire construction project. All of that for 6 people. Not a city, not a colony. 6 people in low Earth orbit, relatively close to the Sun by cosmic standards, still bathed in the warmth of a nearby star's radiation. And the thermal problem is already this large, this expensive, this unforgiving. Now consider what this means at larger scales. Forget astronauts and spacecraft for a moment. Think about the spaces between stars. The nearest star to our own Sun is Proxima Centauri, sitting roughly 4 light-years away, a distance that, translated into more familiar units, is something in the range of 24 trillion miles. The average separation between neighboring stars in our region of the galaxy is close to that same figure. 4 light-years, 24 trillion miles of emptiness between each furnace and the next. Any object drifting through that void has no thermal management system, no radiators, and no heaters cycling on and off every 90 minutes to compensate for the shift from light to shadow. It simply floats, and whatever heat it contains, it slowly radiates away, photon by photon, with almost nothing arriving from outside to replace what it loses, which raises the question the numbers have been building toward. How cold, exactly, does something become when it has been losing heat for long enough, with nothing to stop it? The answer begins with your own body. Right now, wherever you are, your skin is radiating heat into the space around you. Not in some metaphorical sense, not as a figure of speech, literally, physically radiating it, emitting infrared light the way every object with a temperature above absolute zero emits electromagnetic radiation. You are a warm object in a cooler environment, and because of that, yet you are constantly shedding energy in the form of light you cannot see. The room around you radiates some energy back toward you, the walls and the floor and the air all contributing their own infrared glow. And in that exchange, you reach an equilibrium. You lose heat to your surroundings, and your surroundings return some portion of it. And the net result is a body temperature you can maintain without difficulty. The exchange is continuous, invisible, and so ordinary that it never once occurs to you it is happening. Now remove the room. Remove the walls, the floor, the air, the building, the planet beneath it. Place yourself, or any object, a rock, a piece of metal, a body, in the void between stars, 4 light-years from the nearest sun, adrift in the emptiness that constitutes most of the galaxy's volume. The object still radiates. Whatever heat it contains still bleeds outward as infrared light, photon by photon, each one carrying a small quantity of energy away from the object and out into the dark in every direction simultaneously. This process does not stop simply because there is nothing around to receive the energy. The physics does not care about context or location. A warm object radiates. That is what warm objects do. But here is where the situation becomes unlike anything in ordinary experience. In interstellar space, where the density of matter has dropped to something in the range of 1 atom per cubic centimeter or possibly less, there is almost nothing radiating back. No walls, no floor, no atmosphere returning the favor. The vast majority of the energy the object emits travels outward without interruption, crosses distances that dwarf anything in our solar system, and disperses into a void that offers nothing in exchange. The exchange that keeps your body in equilibrium, the constant mutual radiation between you and your surroundings, has no partner on the other side. You send energy outward, and the universe, for the most part, does not reply. The cold of space is not an assault, it is an abandonment. The object does not freeze in the way water freezes, suddenly and completely at a defined boundary. It drains, slowly, incrementally, with the patience that only a universe 13.8 billion years old can demonstrate. It loses warmth. the only way anything can lose warmth in that environment, photon by photon, each one a departure that will never return. And the cooling is relentless in the way that only asymptotic processes can be relentless, which is to say that it never fully arrives at its destination. The temperature falls and falls and falls, approaching a minimum the way a curve approaches a line on a graph, getting closer with every increment but never, mathematically, quite touching it. Absolute zero, the complete absence of thermal motion, the point at which matter has surrendered every quantum of energy it is permitted to surrender, sits as the theoretical floor, and in interstellar space, an object drifts toward that floor, the way sediment drifts toward the bottom of a still lake, continuously sinking, never quite settling. This matters because it changes the nature of what cold means in this context. Cold, in ordinary life, is something you encounter, a wind, a surface, a plunge into water. It reaches you. It acts on you through the mechanisms of conduction and convection, through contact and flow, and its aggression is immediate and legible. You feel it. Out there, none of that aggression exists. There is no wind, no surface, no medium carrying the cold toward you. There is only the quiet exit of energy you already possess, and the failure of anything to replace it. The temperature an object reaches in interstellar space is not imposed from outside. It is arrived at from within. At the warmth leaves, and nothing comes to fill the space it occupied, and what remains is a kind of thermal solitude that has no analogue in any environment your body has ever occupied. But here is the thing that the straightforward version of this story would miss entirely. The thing that keeps the cooling from completing itself, even across billions of years of emptiness. The floor is not absolute zero. Something prevents it. Some tiny trickle of incoming energy, almost immeasurably small, fills the void from every direction at once, so uniformly and so completely that there is nowhere in the observable universe where it is not present. Even in the darkest, most isolated regions between the galaxies, even in the voids that stretch for hundreds of millions of light years without a single star to warm them, so this faint background radiation exists, arriving equally from every point of the sky simultaneously, so that no direction is colder than any other and no shadow is deeper than any other. The object drifting in interstellar space does not drain to nothing. It drains toward the temperature set by this radiation, and then it stops, held at that floor by the faintest possible whisper of incoming energy keeping exact pace with the last traces of what it loses. That floor is set by the only source of radiation that permeates all of space, everywhere in the universe without exception, the faintest, most ancient light in existence. And that source is old in a way that the word old cannot carry without help. And to understand what sets the floor at 2.725 Kelvin, 2.725 degrees above the coldest temperature that physics permits, you have to go back not just before recorded history, not just before the formation of the Earth, not just before the first stars ignited, but back to the first fraction of the first second of the universe's existence, when everything that would eventually become the observable cosmos was compressed into a volume so small and a temperature so extreme that the numbers required to describe it have ceased to carry any intuitive meaning at all. The universe did not begin cold. It began at temperatures exceeding 10 trillion degrees, and a number so far beyond ordinary experience that the only honest thing to say about it is that it places you in a register where human language was never designed to operate. Every unit of measurement we use for heat, the degree on a thermometer, the reading on an oven dial, the temperature of a candle flame, was built to describe conditions that exist in an extremely narrow band near the bottom of the thermal scale. 10 trillion degrees is not a larger version of something familiar. It is a different category of reality entirely. At 1 second after the Big Bang, just 1 second, when the universe was younger than the interval between one heartbeat and the next, the temperature had already fallen to approximately 10 billion degrees. Consider what that single number requires. In 1 second, the universe had cooled from something beyond all thermal description to 10 billion degrees, which is itself hotter than the interior of nearly any star that exists today. Stellar cores, where hydrogen fuses into helium under pressures and temperatures that would vaporize any material we have ever manufactured, reach temperatures on the order of 15 to 20 million degrees. The 1 second old universe was running at nearly 1,000 times that. 1 second old. The cooling was not gradual in any human sense. It was catastrophic, and it was continuous, and it would not stop. In the first few minutes, during the interval stretching from roughly 3 minutes to approximately 20 minutes after the Big Bang, the temperature had dropped far enough that something consequential could happen. Protons and neutrons, which had been slamming together and breaking apart in a thermal chaos too violent for any structure to survive, could now fuse and hold. For this brief window, this roughly 17-minute period that determined the chemical composition of the entire observable universe, the cosmic forge was open. When it closed, when the temperature fell below the threshold where fusion could continue, the inventory was locked in permanently. 75% of all the ordinary matter in the universe became hydrogen. 25% became helium. Trace quantities of lithium and a few other light elements completed the accounting. The oldest stars we can observe, the ones that formed when the universe was young and nearly nothing heavier than helium existed, still carry these proportions in their atmospheres, and a preserved record of those 17 minutes written in the elemental ratios of ancient suns. But atoms themselves did not yet exist. Protons and electrons, the components of hydrogen, could not combine into stable atoms because the temperature was still too high, still energetic enough that any electron attempting to settle into orbit around a proton was immediately knocked loose by the radiation, filling all of space. The universe remained, for hundreds of thousands of years, a dense opaque plasma, a fog of charged particles and photons in constant violent interaction, impenetrable to light, a state where no photon could travel more than a short distance before being absorbed and re-emitted. This continued for 380,000 years, and then, and over a period that was brief by cosmic standards but would still dwarf all of recorded human civilization, the temperature fell below 3,000 Kelvin, and something that had never happened before happened for the first time. Electrons settled, protons captured them, hydrogen atoms formed and held, and in forming, they stopped interacting with the photons that had been trapped in that plasma for nearly 400,000 years. The fog cleared, the universe for the first time became transparent, and every photon that had been locked in that plasma was suddenly free to travel, released all at once from every point in space simultaneously in every direction at once, an eruption of light that has been traveling ever since. Those photons are the cosmic microwave background, and they are the light released at that moment of clearing, and they have been journeying through the expanding universe for 13.8 billion years. But the universe has not been sitting still. It has been expanding, stretching the fabric of space itself, and as space stretches, the wavelengths of light traveling through it stretch along with it. The photons released at recombination had wavelengths shorter than 1 micrometer, which places them in the near-infrared range, adjacent to visible light, the kind of radiation that would register as a warm red glow if your eyes could have been present at that moment. Since then, the universe has expanded by a factor of approximately 1100, and so those wavelengths have stretched by the same factor, from less than 1 micrometer to more than 1 millimeter, moving them entirely out of the visible spectrum and into the microwave range, which is how they earned their name. The universe's first light is now invisible to human eyes, not because it has gone dark, but because the expansion of space has pulled it into frequencies below what our biology was built to detect, and the temperature carried by that radiation has stretched along with it. 3000 Kelvin, the temperature at which those photons were released, divided by 1100, yields approximately 2.7 Kelvin, 2.725 precisely, as measured by the Kobe satellite, to an accuracy of less than 1,000th of a degree. At that number, 2.7 Kelvin is not an arbitrary property of empty space. It is the thermal fossil of the Big Bang itself, the last faint warmth of an event of unimaginable violence, cooled by 13.8 billion years of expansion into something barely distinguishable from nothing at all. The universe was born in fire and has been surrendering that fire ever since. And 2.7 Kelvin is what 13.8 billion years of surrender looks like. The universe spent almost everything it had in the first few 100,000 years. What remains is the faintest residual warmth, so attenuated by time and expansion that it sits only 2.7 degrees above the theoretical minimum the laws of physics allow. 2.7 Kelvin. The question that remains is what that number actually means in terms your body can feel. 2.7 Kelvin. The number has been named. Its origin traced through 13.8 billion years of expansion. Its meaning located in the last faint warmth of a universe that was once unimaginably violent. But there is a difference between understanding a number and feeling it. The number 2.7 sits quietly in the mind, and the mind accepts it without protest, because the mind has no instinct for temperatures this far removed from anything it has ever encountered. So the only way to make it real is to build a ladder down from the world you know, rung by rung, until the ladder runs out of material and you are left looking at how far remains. Start with something familiar in an industrial sense, even if not in a personal one. Liquid nitrogen, the substance used in laboratories and medical facilities and food processing operations around the world, boils at 77 Kelvin. 77 Kelvin is cold in a way that commands respect. It will freeze tissue on contact. It will shatter rubber. A flower dipped in it becomes brittle as glass and disintegrates when dropped. Plunge your hand into it and the damage begins in seconds, irreversible and progressive. 77 Kelvin is the kind of cold that ends biological processes without hesitation, the kind of cold that your body has no defense against, no physiological response adequate to, no survival instinct built for, because nothing in the environment your species evolved in has ever been anywhere close to 77 Kelvin. And the cosmic microwave background is 29 times colder than that, not slightly colder, not incrementally more extreme, 29 times colder than the temperature at which nitrogen, a gas that makes up 78% of the air in the room around you, becomes a liquid. If 77 Kelvin already sits so far below anything your body can survive that the comparison feels almost theoretical, then multiplying that distance by 29 does not produce a number your intuition can track in any meaningful way. It produces something that requires a different kind of reckoning entirely. But the ladder goes further. There is a colder substance, one that sits much closer to the floor of what physics permits. Liquid helium boils at 4.2 Kelvin, yet this is a temperature so low that achieving it in a laboratory requires extraordinary equipment and careful technique, because almost nothing in the known universe is cold enough to cool helium to a liquid at standard pressure, except the deliberate application of advanced refrigeration technology. 4.2 Kelvin is used in superconducting magnets, in research instruments designed to detect signals so faint that any thermal noise would overwhelm them, in the hardware inside the most sensitive detectors we have built. It represents an extreme that human civilization spent most of its history unable even to approach, and only reached in the last century through sustained scientific effort. 4.2 Kelvin is the kind of cold that exists, in any practical sense, only in carefully controlled spaces inside specialized machines. So the cosmic microwave background is colder than that too, not by a factor of 29 this time, but the background radiation that fills all of space, permeating every void and every galaxy and every cubic centimeter of the universe simultaneously, sits below the boiling point of liquid helium. The number is 2.725 and 4.2 is higher. That gap, 1.5 Kelvin, a number that sounds trivially small, represents the difference between the coldest engineered environments human beings have managed to construct and the ambient temperature of the universe itself. The universe, simply by existing, is colder than our best refrigeration. Now come back to Earth. Come back to the surface of this planet, to the coldest place any thermometer has ever recorded in all of human history, and in all of the centuries we have been measuring such things. On July 21st, 1983, at the Soviet research station Vostok in Antarctica, the temperature dropped to negative 89.2 degrees Celsius. That number, converted into Kelvin, is 184. Sit with that number for a moment. The coldest temperature any human being has ever experienced on Earth is practically tropical by cosmic standards. 184 Kelvin, the most extreme cold this planet has ever recorded, in a location where people were present to observe it. A cold so severe it would kill an unprotected person in minutes and freeze fuel lines and crack steel and make the air itself behave strangely. That temperature is 68 times warmer than the ambient temperature of open space. 68 times. Not a rounding error, not a marginal distinction. The worst cold this world has ever produced, the reading that stands as the absolute outer boundary of terrestrial experience with low temperature, is 68 times higher on the Kelvin scale than the temperature of the universe's background radiation. Everything your species has ever felt, measured, survived, or died from in terms of cold, every blizzard, every tundra winter, every polar expedition, every catastrophic freeze, all of it takes place in a thermal range that, by the universe's standards, barely qualifies as cold at all. Earth's entire history of cold, from the mildest winter morning to the most extreme Antarctic record, compresses into the upper end of the temperature scale when set beside 2.7 Kelvin. Our coldest nightmare is the universe's room temperature, and that room extends in every direction without interruption, across distances so large that the journey from here to the nearest star takes light itself 4 years to complete. The cosmic microwave background does not thin out at the edges of the solar system. It does not weaken as you pass beyond the orbit of Neptune. It fills the voids between galaxies, the spaces between galaxy clusters, the enormous empty regions that stretch hundreds of millions of light years across, without a single significant source of heat. 2.7 Kelvin is not a local curiosity. It is the baseline. It is what the universe defaults to when nothing is present to heat it. But something sometimes is. Stars burn. Accretion disks surrounding black holes reach temperatures that make stellar cores seem moderate. The universe contains, is scattered across its vast cold expanse, sources of heat so extreme they strain the vocabulary we have built for describing temperature. The question is how those burning exceptions relate to the freezing rule. How much of the universe is touched by that heat, and how much sits undisturbed at 2.7, in the dark, waiting. The signal that confirmed all of this, the 2.7 Kelvin flaw, the cooling history of the universe, the thermal fossil of the Big Bang that fills every void in every direction, was not discovered by a team of cosmologists hunting for it with purpose. It was discovered by accident in New Jersey by two engineers who were trying to do something else entirely and who spent months assuming the noise ruining their work was caused by pigeon droppings. Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey in 1964. Their assignment was practical rather than philosophical. They were calibrating a large horn-shaped antenna that had been built to track the Echo satellite communications program, and they were trying to characterize the noise floor of the instrument so it could be used for precise radio astronomy. The antenna itself was an unusual structure, shaped something like a massive ear pressed against the sky, designed to receive microwave signals with extraordinary sensitivity. That sensitivity as it turned out, would be the thing that changed everything. When Penzias and Wilson began their measurements, they found something they could not account for. There was a persistent uniform hiss in their data, as a steady, low-level noise that appeared regardless of which direction they pointed the antenna. It did not vary with the time of day, which would have suggested a source on Earth or in the atmosphere. It did not vary with the season, which ruled out something in the solar system. It came equally from every part of the sky they examined, which eliminated any single astronomical source. The signal was, in every measurable sense, omnidirectional, and it corresponded to a temperature of approximately 3.5 Kelvin. They had no explanation for what they were hearing. The engineers did what careful people do when confronted with an anomaly. They looked for the mistake. They checked their equipment. They examined every component of the antenna system for faults. And then they found the pigeons. A pair of birds had taken up residence inside the horn antenna and had left behind what Penzias and Wilson described, with admirable restraint in their published notes, as a white dielectric material, a coating of droppings that had accumulated along the interior surfaces of the antenna. It was a reasonable hypothesis that this material might be introducing an electrical interference that was producing the spurious signal. So they cleaned it out. They removed the birds, they scraped the antenna clean, and they took new readings. The hiss remained, unchanged, at the same intensity from every direction, corresponding to the same temperature. The universe did not care about their cleaning efforts. They were, at this point, genuinely stuck. They had a signal they could not explain and could not eliminate, and it was threatening to undermine the precision of everything they were trying to accomplish. What happened next is one of the more remarkable coincidences in the history of science, and it was not really a coincidence at all, which makes it more remarkable still. Roughly 40 miles away, at Princeton University, a physicist named Robert Dicker had been working with a young theorist named Jim Peebles on a completely separate line of reasoning. Peebles had calculated, from first principles, working through the mathematics of what the early universe must have been like in its first moments of existence, and that the Big Bang should have left behind a detectable afterglow, a field of radiation that had been cooling for the entire age of the universe and should now register at a temperature of just a few Kelvin. Dicker's group was, at the moment that Penzias and Wilson were puzzling over their pigeon drop problem, actively building an antenna of their own to search for exactly this signal. Penzias reached Dicker by telephone. The Princeton team listened to the description of the unexplained hiss, the temperature, the uniformity, the impossibility of eliminating it. And Dicker, by most accounts, put down the receiver, turned to his colleagues, and said, with the particular calm of someone who has just understood something very large, that they had been beaten to it. Yea, the annoyance that had persisted through months of equipment checks and bird removal and component rebuilding was not noise at all. It was the oldest light in the universe, stretched by 13.8 billion years of cosmic expansion into microwave frequencies, arriving at a horn antenna in New Jersey at a temperature of approximately 3.5 Kelvin, waiting patiently to be understood. Penzias and Wilson published their measurement in 1965. Dickey and Peebles published their theoretical prediction alongside it. In a companion paper, in the same journal issue, the 2.7 Kelvin number that has appeared throughout this account, the precise value that cosmologists now cite as the temperature of the cosmic microwave background, was not what Penzias and Wilson measured. Their instruments were cruder, and 3.5 Kelvin was the best they could do with the tools available. But the nature of the signal was unmistakable, and the rough measurement was close enough. They had found the thermal echo of creation with an antenna designed for satellite communication, cleaned by hand and contaminated for a time by birds. In 1978, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics for that discovery. What their instrument had heard, crudely, at 3.5 Kelvin, was confirmed by that measurement as real. But the full precision of that signal, the exact shape and temperature of the oldest radiation in the universe was still a question that remained open. A rough reading taken in a New Jersey field was enough to establish that the signal existed, and it was not enough to tell us everything the signal contained. That would require something far more powerful than a repurposed satellite antenna, and it would come in the decades that followed when we turned instruments of genuine precision toward that ancient hiss and discovered it was not just a temperature, but an entire archive. And what those instruments found, when we finally turned proper precision toward that signal, is that the rough measurement Penzias and Wilson had made was not the end of the story, but the very beginning of it. 3.5 Kelvin was enough to prove the signal existed. It told us almost nothing about what the signal contained. The real work of decoding the oldest light in the universe began in 1989, when NASA launched a satellite called COBE, the Cosmic Background Explorer, into orbit, pointed it at the sky in every direction, and asked a more demanding question than any ground-based antenna had been able to ask. Not just, is the signal there? But, what is its exact shape, its precise temperature, its fine structure across the entire sky? The answer came back with a precision that remains difficult to absorb even now. COBE confirmed that the cosmic microwave background is, to the limits of what those instruments could measure, a perfect blackbody spectrum at 2.725 Kelvin, with an uncertainty smaller than 1,000th of a degree. To understand what that means, consider that most temperature measurements we encounter in daily life carry uncertainties of at least 1/10 of a degree and often more. Medical thermometers, weather stations, laboratory instruments, they all operate in that range. COBE was measuring the temperature of the entire observable universe and arriving at a figure accurate to within a fraction of what even careful instruments on Earth can routinely achieve. The number was not an approximation. It was a nail driven through the floor. But the more consequential discovery was not the temperature itself. It was what lay beneath the uniformity. Because COBE also detected, embedded within that nearly featureless glow, fluctuations in temperature, tiny variations from one region of sky to another, differences so small that they amounted to 1 part in 100,000. To make that concrete, if you painted a wall the color that represents the average temperature of the CMB and then tried to represent the fluctuations on that same wall, you would be looking for differences smaller than the width of a single brushstroke made by a single hair from the finest brush you could find, across a surface the size of a house. The background would look absolutely uniform to any eye ever made. And yet, those differences are there, and those differences are everything. Those fluctuations are the seeds of all structure in the observable universe. The galaxies you see when you look at photographs taken by orbital telescopes, the long filaments of matter stretching across hundreds of millions of light years, the great voids between them where almost nothing exists. All of it traces its origin to those 1 in 100,000 temperature variations printed into the fabric of the universe when it was less than 400,000 years old. The uniformity of the CMB tells you that the early universe was extraordinarily smooth. The tiny variations within that uniformity tell you that it was not perfectly smooth, and that imperfection, amplified over billions of years by gravity, became everything you have ever seen. The signal that Penzias and Wilson heard as an annoying hiss in New Jersey contained, buried inside it, the blueprint of the entire large-scale structure of the cosmos. WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, it took that blueprint and read it with 35 times the angular resolution that COBE had achieved. The difference between a blurred outline and a detailed map. What WMAP returned was not just a sharper picture, but a set of numbers that pinned the history of the universe to a degree of precision that no other instrument in any field of science had matched for questions of this scale. The age of the universe, 13.77 billion years, with an uncertainty small enough that the number itself felt almost reckless in its confidence. And nested within that age measurement was a full accounting of what the universe is actually made of, derived not from any direct observation of the matter itself, but from the way the temperature fluctuations in the ancient light were distributed across the sky. The result was this: ordinary matter, the atoms that make up stars, planets, oceans, your body, every object that has ever been built or grown or named, constitutes 4.6% of the total energy content of the observable universe. That is not a small fraction. That is a rounding error. The remaining 95.5% of everything that exists divides into two categories that we do not fully understand. Dark matter, which interacts with gravity and therefore shapes the large-scale structure of how galaxies form and cluster, accounts for roughly 23%. It outweighs ordinary matter by a ratio of approximately 5:1. For every gram of substance that can absorb light, emit light, or be touched, yet as there are roughly 5 grams of something that does none of those things, and that no laboratory on Earth has ever directly detected. And then there is dark energy, the term we use for whatever is causing the expansion of the universe to accelerate rather than slow, and that accounts for approximately 72%. The honest answer to the question of what dark energy actually is remains that we do not know with any precision. We have measured its effects with extraordinary care. We have given it a name. Its fundamental nature is a question that does not yet have an answer. The precision of the measurement is extraordinary, but the interpretation of what we are measuring rests on frameworks we are still testing. The European Space Agency's Planck satellite, launched in 2009 across 9 separate frequency bands, had refined these numbers further still, adjusting the age of the universe from UMAP's 13.77 billion years to 13.798 billion years, a difference of roughly 20 million years on a timeline of nearly 14 billion, which is itself a testament to how fine the instrument's blade had become. Planck also confirmed with high confidence the predictions of cosmic inflation, a theory proposed in 1980 by a physicist named Alan Guth, which holds that the universe underwent an extraordinary expansion in its first instance of existence, growing by a factor of at least 10 to the 26th power in something like 10 to the negative 36th of a second. That is a number so far outside normal experience that the words used to describe it stop conveying meaning in the ordinary sense. And what inflation explains is why the CMB is as smooth as it is, why regions of the early universe that should have had no causal contact with one another, no time to exchange energy or equalize temperature, nonetheless arrived at almost exactly the same temperature from every direction in the sky. Planck also confirmed that the universe is geometrically flat, which has implications for its total extent that reach far beyond what any telescope has ever seen. The reading of the ancient light did not just tell us about the past, it told us about the shape of reality itself. And so, what began as a persistent hiss that 2 engineers in New Jersey could not explain, a signal they tried to eliminate, that turned out to be ineliminable, not because their equipment was flawed, but because it filled the entire universe, became, and in the decades that followed their discovery, the most precisely characterized signal in the history of cosmology. Not just a temperature, but a map. Not just a map, but a composition. Not just a composition, but a geometry. The faint microwave whisper that arrives at every point on Earth from every direction in the sky contains, encoded in its fine structure, more information about the origin and nature of reality than any other measurement we have ever made or are likely to make in the foreseeable future. It is the oldest data we will ever have access to. Nothing will ever be older, because nothing before recombination can reach us. The universe before that moment was opaque, and the CMB is the earliest edge of what can be seen. But there is something else to say about this signal, is something that sits alongside all that precision and all that information and qualifies it in a way that the instruments themselves cannot measure. The CMB is not static. It is not a fixed record sitting at 2.725 Kelvin, waiting for future generations to read it more clearly. The universe continues to expand. Space continues to stretch. And as it does, the photons of the cosmic microwave background are stretched along with it, their wavelengths growing longer, their energies diminishing, their effective temperature dropping further still. The signal that Penzias and Wilson first detected, that COBE measured with such extraordinary care, that WMAP and Planck decoded into the blueprint of the cosmos, that signal is cooling. The archive is not being preserved. It is being diluted, slowly, by the same expansion that stretched the original fire of creation into the microwave whisper we detect today. And that cooling is not a future event waiting to happen at some distant point in time. It is happening now, in the same way that the expansion of the universe is happening now, continuously, without pause, without any mechanism that could reverse it. The 2.7 Kelvin floor that took decades of precise instrumentation to measure and characterize is not a fixed boundary. It is a value on a slope that descends, gradually but without exception, toward a temperature that approaches absolute zero without ever quite reaching it. Consider what this means in concrete terms. The universe today is approximately 13.8 billion years old, and the background radiation has cooled to 2.725 Kelvin. But the universe will not stop expanding at its current size. It will continue to grow, and as it grows, those ancient photons continue to stretch. When the universe is twice its current size, not twice as wide in some local sense, but twice as large in every direction across all of space, the wavelengths of the cosmic microwave background will have stretched by a corresponding factor, and the effective temperature of that radiation will drop to approximately 1.4 Kelvin, half of what it is today, not in a distant era measured in billions of years, but as an inevitable consequence of the expansion that is already underway, already measurable, already confirmed by every cosmological instrument we have ever built. The afterglow of creation, which was already colder than anything your body has ever produced or could survive, will be colder still. And after the universe doubles again, it will be colder than that. And again after that, each doubling pressing the floor lower, each era of expansion extinguishing a little more of what remains of the original fire. There is no rescue from this trajectory. The same dark energy that is accelerating the expansion of the universe, that mysterious component making up roughly 72% of the total energy budget of the cosmos, whose nature we cannot yet explain or measure directly, ensures that the expansion does not slow down as it might if gravity were the only force involved. It accelerates, which means the stretching of those ancient photons accelerates with it. The floor is not just sinking, and it is sinking faster with each passing age of the universe, pressing toward a temperature so close to absolute zero that the difference between the background radiation and nothing at all becomes, for most practical purposes in the universe's future, negligible. The universe was born in fire. It has been surrendering that fire since the first fraction of a second, and it will continue surrendering it for longer than any number we have used in this conversation can describe. But, and this is the moment where the picture has to stop and hold, because something important has been quietly missing from it. The universe is not uniformly at that floor. Not right now, in this present era, at this particular point in cosmic time. The temperature of 2.7 Kelvin describes the background, the baseline, and the radiation that fills every cubic meter of space in every direction without exception. It does not describe everything that exists within that space, because scattered across the vast, cold dark, separated by distances so enormous they make the emptiness feel structural rather than accidental, there are objects burning at temperatures that seem to belong to an entirely different universe altogether. The core of our own sun, the nearest star, the one whose light takes 8 minutes to reach the room you are sitting in, burns at approximately 15 million degrees. Not 15 million degrees the way that large numbers sometimes get thrown around loosely in descriptions of distant phenomena. 15 million Kelvin, measured through helioseismology and confirmed by the energy output at the surface, by the neutrino flux that passes through every square centimeter of the Earth every second, by the physics of nuclear fusion that requires temperatures of precisely that magnitude to sustain itself. At 15 million degrees, hydrogen nuclei are moving fast enough and close enough together that the electromagnetic repulsion between them, the force that keeps protons apart under ordinary conditions, is overcome, and they fuse. 2 protons combine, and then 2 more, and the process releases the energy that eventually reaches Earth as the light you have felt on your skin on a summer afternoon. The Sun has been sustaining this process for approximately 4.6 billion years and has enough hydrogen remaining to sustain it for roughly 5 billion more. That is the temperature of a single star's core, one of an estimated 200 billion stars in this galaxy alone. And the Sun, though vast by human scale, is not among the most extreme examples. Blue supergiant stars burn at surface temperatures approaching 11,000 degrees, surface temperatures, not cores, and their cores reach proportionally higher values. When those massive stars exhaust their fuel and collapse, the resulting supernova briefly achieve temperatures near 100 billion degrees, releasing in a matter of seconds more energy than the Sun will emit across its entire 10 billion year lifespan. Around collapsed objects and black holes, material falling inward forms accretion disks where gravitational compression and friction drive temperatures into the tens of millions, sometimes hundreds of millions, as sometimes billions of degrees, higher than stellar cores, achieved not by nuclear fusion, but by the sheer violence of matter falling toward a singularity. These are the exceptions. They are spectacular, and they are real, and they burn at temperatures that dwarf anything in the story of human coldness that this journey began with. Stars are the local reversals of the cosmic cooling, fierce, furious, genuine. The question that follows naturally, the question that the existence of these burning exceptions demands, is how much of the universe they actually fill, how much of all the space in all the cosmos sits within reach of that heat, bathed in that light, elevated above the 2.7 Kelvin floor by the presence of something burning nearby. The hot exceptions are catalogued. What remains is to measure them against the rule. To measure what the burning exceptions actually amount to, you have to begin with the individual star, not as an abstraction, not as a point of light in a photograph, but as a physical object with a surface, a volume, a temperature you could assign a number to. And the numbers, when you take them seriously, are genuinely extraordinary. The surface of our own Sun sits at approximately 5,500 degrees Celsius. That is the temperature of the layer of the Sun that produces the light falling on every field and ocean and rooftop on Earth. It is hot enough that no material humanity has ever manufactured could survive contact with it. Hot enough that the distinction between solid and liquid and gas collapses entirely into a churning plasma of stripped electrons and bare atomic nuclei. And yet the surface is, by stellar standards, the cool part. The core, as has already been established on this journey, burns at 15 million degrees. Between the surface and the core, across a distance of roughly 430,000 miles of layered gas and plasma, the temperature climbs from 5,500 to 15 million, a gradient that represents one of the most extreme transitions in temperature that occurs naturally anywhere in the solar system. Every second, the nuclear reactions sustaining that gradient convert approximately 4 million tons of mass directly into energy, not burning it, not combusting it, but annihilating it, converting matter itself into radiation via Einstein's equation, at a rate of 4 million tons per second, hour after hour, year after year, are across a lifespan that will reach roughly 10 billion years total. That single star, the Sun, spans 865,000 miles in diameter. 1.3 million Earths could fit inside its volume. The distance from its surface to Earth is 93 million miles, which light covers in 8 minutes, but which would require more than a century of continuous driving at highway speed to cross by car. This is a significant, weighty, enormous object by any scale that a human being can genuinely process. But the Sun is not among the most extreme examples of stellar temperature. Blue supergiants like Rigel, a star visible from Earth as a bright point in the constellation Orion, maintain surface temperatures exceeding 11,000 degrees Celsius, meaning their outermost visible layer, the part analogous to the Sun's surface, burns at twice the temperature of the Sun's surface. At the other end of the stellar spectrum, red dwarf stars burn at surface temperatures around 3,000 degrees Celsius. They are dimmer, cooler, smaller, and they are by far the most numerous stars in the galaxy, comprising roughly 70% of all stars in the Milky Way. The Sun, the brilliant yellow star at the center of our solar system, is actually above average in temperature and size. The typical star in this galaxy is a red dwarf, quiet and dim, burning at 3,000 degrees, and many of them will continue burning for 10 to 15 trillion years, durations roughly 1,000 times longer than the current age of the universe itself. Not one red dwarf that has ever formed has yet had time to die. So take this inventory of stellar temperatures seriously. 3,000 degrees at the cool end, 5,500 at the solar surface, 11,000 at the blue supergiant surface, 15 million in the solar core, and higher still in more extreme objects. These are real temperatures, attached to real objects, burning in the sky above you right now. The question is what all of this fury amounts to, spatially. The question is how much room these burning objects actually occupy in the universe. And this is where the picture changes. Quietly, but completely. Consider an analogy. Shrink the Sun, all 865,000 miles of it, all 1.3 million Earth volumes of it, or all 15 million degrees of its core and 5,500 degrees of its surface. Shrink it down to the size of a ping pong ball, roughly 1.5 inches in diameter. At that scale, the Earth becomes a microscopic speck, invisible to the naked eye, orbiting about 5 feet away. The entire solar system, out to its outermost regions, compresses to something roughly the size of a large room, and the nearest star, Proxima Centauri, at a distance of approximately 4.25 light-years, roughly 25 trillion miles away, becomes, at this same scale, another ping-pong ball sitting approximately 720 miles away. Between those two ping-pong balls, both burning at temperatures no material on Earth could survive, both consuming millions of tons of mass per second in nuclear fire, sits 720 miles of empty scale space. No atmosphere, no matter of any consequence, nothing but the near absolute zero vacuum through which the cosmic microwave background quietly hums. And if you wanted to fill that 720 miles of space between those two ping pong balls with more ping pong ball suns, end to end, you would need approximately 30 million of them, 30 million suns, shrunk to ping pong ball scale, packed together without gaps, to bridge the distance between our sun and its single nearest neighbor. Sit with that distance. 2 ping pong balls, 720 miles apart, 30 million more between them if you wanted to close the gap. This is not an unusual gap in the galaxy, selected for its emptiness. Yet this is the most crowded stellar neighborhood we know, the star closest to us, our nearest companion in the galaxy. This is what stellar density looks like at its most locally favorable, and it reduces every burning, violent, 15 million degree furnace to a speck so vanishingly small that the emptiness between them is not incidental. The emptiness is the dominant fact. The 200 billion stars in the Milky Way, each one a genuine, ferocious, nuclear-powered engine of heat and light. All of them, together, leave the vast majority of the galaxy's volume untouched. The question that follows is whether 200 billion vanishingly tiny specks, scattered across a volume of space too large to visualize, add up to anything at all against the cold dark between them. The answer to that question, it turns out, is available, not as a feeling, not as an impression, but as a number, and the number is precise enough to settle the matter entirely. The Milky Way contains somewhere between 200 billion and 400 billion stars. The exact count remains uncertain. We cannot see every star in our own galaxy with clarity because we sit inside it, surrounded by gas and dust that obscures the view. But the order of magnitude is well established. Hundreds of billions of stars, each one a nuclear furnace, each one converting mass into energy every second of every day, each one radiating heat and light into the space around it. This is a real quantity of fire. It is not nothing. And if you multiply it across the observable universe, which contains an estimated total of roughly 10 to the 24th stars, that is, roughly a trillion stars, a number so large that no comparison does it full justice, then the total amount of burning matter in the cosmos seems, at first, like it should amount to something thermal, a trillion fires. Surely that fills some meaningful portion of space with warmth. But now, consider what those fires actually occupy. The Milky Way itself spans roughly 100,000 light-years in diameter and is perhaps 1,000 light-years thick at its central disk. And when you work through the geometry, its total volume comes to approximately 8 trillion cubic light-years. 8 trillion is a number that sounds enormous. It is enormous, by any standard rooted in human experience. But the Milky Way is one galaxy among hundreds of billions of galaxies in the observable universe. And the observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extending outward in every direction to a radius of approximately 46.5 billion light-years, has a total volume of approximately 4.2 times 10 to the 80th cubic meters. That is 4.2 followed by 80 zeros. And when you calculate the total volume occupied by all the stars in the observable universe, not the galaxies, not the gas, not the dust, but the actual burning stellar bodies themselves, that volume comes to approximately 10 to the 51st cubic meters. Now divide. 10 to the 51st divided by 4.2 times 10 to the 80th gives you a fraction of approximately 10 to the negative 29th. And that is the share of cosmic volume occupied by all the stars that have ever burned or are burning right now. 10 to the negative 29th. The notation is compact, which makes it easy to pass over, but do not pass over it, because this number is the entire answer to the question of whether stellar fire amounts to anything against the cold. 10 to the negative 29th is less than 1 billionth of 1 billionth of 1 billionth. If you took the entire cosmic volume and divided it into a billion equal pieces, then took one of those pieces and divided it into a billion more, then took one of those and divided it again into a billion more, you would still not have a piece small enough to represent the share that stars occupy. You would need to divide it one more time, and the stars would not even fill that final, impossibly subdivided fragment. There is no comparison that comfortably contains this number. It sits beyond the range where analogies remain useful, and yet the attempt is still worth making, because the alternative is to let the notation absorb the weight without feeling it. Consider that the air in the room you are sitting in contains hundreds of billions of molecules in every cubic centimeter. The density of matter in familiar space is almost incomprehensibly high by cosmic standards. Now consider that if you took all of that ordinary density, all of that comfortable packed-in molecular richness, and asked what fraction of cosmic volume it represents, the answer would still be negligibly, irrelevantly small. Stars are denser still, but there are so few of them. and space is so indifferently vast that the arithmetic does not shift in any direction that matters. 1 trillion stars, each one of them a genuine furnace, each one converting millions of tons of mass into energy every second, each one radiating temperatures that would vaporize any material we have ever manufactured, occupy a fraction of the universe so small that if you rounded it to zero, not a single cosmological calculation would change. No equation, no model, no prediction. The error introduced by ignoring all stellar volume entirely would be smaller than the rounding errors already present in our best measurements. This is not an exaggeration made for effect. It is a straightforward consequence of arithmetic, and the temperature that fills the remaining volume, the 4.2 times 10 to the 80th cubic meters of space from which the stars are absent, remains, as it has since recombination, very close to 2.7 Kelvin. Not warmer in the regions near galaxies, not meaningfully heated by the collective output of the stellar populations within them, but sitting at that near absolute zero baseline that the cosmos has maintained since the universe was roughly 380,000 years old. 2.7 Kelvin is not a cold pocket in an otherwise warm universe. 2.7 Kelvin is the room temperature of the cosmos, against which every burning exception, every stellar core, every supernova, every accretion disk-spinning material at temperatures of millions and billions of degrees, registers as a local, a temporary, vanishingly small departure. The hot objects are spectacular and real, but they occupy a fraction of cosmic volume so negligibly small that rounding it to zero would not meaningfully change any calculation in cosmology. But there is one more candidate for warmth that has not yet been examined, and some who have followed this argument to this point will feel it as a remaining foothold. Between the galaxies, not inside them, not near any star, but in the vast stretches of intergalactic space, there is a diffuse medium of gas, a thin haze of baryonic matter that exists in the enormous volumes between galaxy clusters. Observations of this intergalactic medium suggest that large portions of it reach temperatures of millions of degrees, heated by shock waves from ancient galactic collisions and the outflows of enormous black holes. Millions of degrees, that is hotter than the surfaces of most stars, and it may account for a significant fraction of all the ordinary matter in the observable universe. So the question that follows, arriving almost as a form of relief, is whether this vast hot medium finally tips the balance, whether the universe between the galaxies might, in some meaningful sense, be warm after all. The answer to that question depends entirely on what the word hot actually means when applied to a gas. And the distinction that needs to be drawn here is one that most discussions of the intergalactic medium quietly skip over, because following it to its conclusion removes the last available foothold. Temperature, as a physical quantity, is a measure of how fast individual particles are moving. When you heat a gas, you are accelerating its particles, and the particles in the warm-hot intergalactic medium, that diffuse haze of baryonic matter floating in the enormous spaces between galaxy clusters, heated by ancient shock waves and the outflows of supermassive black holes, those particles are indeed moving extraordinarily fast, fast enough to correspond to temperatures of millions of degrees. The number is real. The motion is real. But temperature, by itself, does not tell you how much heat a substance actually contains in a given region of space. For that, you need to know the density. You need to know how many particles are present in each unit of volume. And this is where the intergalactic medium reveals what it actually is. The density of the warm-hot intergalactic medium is, in the most literal sense available to physics, almost nothing. The best measurements suggest something in the range of a handful of particles per cubic meter, not a handful per cubic centimeter, the way ordinary air packs in roughly 25 billion molecules into the volume of a sugar cube, not a handful per cubic kilometer, a handful per cubic meter across the vast stretches of intergalactic space. Consider what that means in terms you can hold in your mind. The room you are sitting in, if it is an average-sized room, contains somewhere around 10,000 trillion air molecules, a number so large it resists any comfortable comparison. If you replaced all of that air with intergalactic medium at the same temperature and maintained those millions of degrees, yet the room would contain perhaps a few thousand particles total. A few thousand particles, moving very fast, occupying the same space where quadrillions of molecules used to be. And heat is not just particle speed. Heat is particle speed multiplied by the number of particles available to transfer that speed to something else. A gas at 1,000,000 degrees with essentially no particles has essentially no thermal energy per unit volume. It cannot warm anything. It cannot be felt. It would not register on any instrument you placed in it, because there is nothing there to press against the instrument's surface. There is no substance to conduct. There is no density of collisions to transfer energy. The temperature is real in the technical sense that the particles present are moving at extraordinary speeds, but the warmth is, and in any practical or physical sense, absent. You could stand in a region of intergalactic medium at 1,000,000 degrees and feel nothing at all, because feeling requires molecules colliding with your body fast enough and frequently enough to transfer energy, and the intergalactic medium cannot provide the frequency. The particles are energetic. They are simply not there. We do not know with precision how much of this gas exists or how it is distributed. The measurements are indirect and the margins are wide. Current estimates suggest that somewhere between 40 and 50% of all the ordinary matter in the observable universe may reside in this diffuse, warm-hot medium, which is itself a striking number, and meaning nearly half of all the atoms that exist between galaxies are in a state that is technically hot and practically invisible to warmth. But the conclusion holds regardless of where within those margins the truth falls. Even if the estimates are generous, even if the true density is higher than the measurements suggest, the gas remains so rarefied that its contribution to the thermal energy of any given volume of space is negligible. Millions of degrees, near zero thermal energy per cubic meter. The two facts coexist without contradiction, and together they produce a result that, once understood, cannot be unfelt. But there is a deeper structural feature of the universe that has been present throughout this entire discussion and has not yet been addressed directly, and it is the one that settles the question permanently. As the cosmos is not organized as a uniform distribution of matter at various temperatures, some regions sparse, some regions denser, spread more or less evenly across all available space. The large-scale structure of the universe is organized into filaments and walls, vast sheets of galaxies stretching across hundreds of millions of light-years. And between those structures lie the cosmic voids. These are not simply low-density regions. They are regions that contain, for all practical purposes, almost nothing at all. No galaxies, no clusters, no significant concentrations of matter, no meaningful sources of heat. They are defined by their emptiness the way a solid object is defined by its edges. The Boötes void, which is among the more studied of these structures, spans roughly 330 million light-years in diameter and contains fewer than 60 known galaxies within its entire interior. 330 million light-years of space and fewer than 60 galaxies. For comparison, a typical region of that same size in a denser part of the universe might contain thousands. The Boötes void is not unusual. It is representative of a category of structure that dominates the cosmos at the largest scales, and the volumes these voids occupy are staggering. Somewhere between 80 and 90% of the total volume of the observable universe is cosmic void. Not slightly more than half, not a majority. Between 80 and 90%. The galaxies, the clusters, the filaments, the intergalactic medium, all of it, every hot object, every warm gas, every heated particle in the known universe, is concentrated in the remaining 10 to 20% of cosmic volume, And even within that minority fraction, most of the space is still the near vacuum that fills the interior of galaxies themselves. When you take all the warm and hot material that exists and express its combined volume as a fraction of total cosmic volume, the result requires scientific notation with negative exponents of a magnitude that makes the stellar fraction seem generous by comparison. A random point in the observable universe is not contested space where warmth and cold compete for dominance. A random point is overwhelmingly, almost certainly, located in a cosmic void, bathed in nothing but the cosmic microwave background at 2.7 Kelvin, with nothing to conduct, nothing to convect, and nothing to radiate any competing warmth across the hundreds of millions of light-years of effectively empty space surrounding it. The universe is not a contest between hot and cold. Cold has already won, totally, across essentially all of space. The hot exceptions are real, and they are the exceptions that every form of life depends on, but they are local, temporary, and structurally irrelevant to what the cosmos is. What the cosmos is, in its overwhelming majority, is cold, not approaching cold, not tending toward cold. Cold, 2.7 Kelvin, saturating 80 to 90% of all the volume that exists, with the remaining fraction occupied by structures so sparse that even their densest members amount to rounding errors in the arithmetic of a universe that has already, without contest, been claimed by cold. What that smallness reveals about the nature of existence and about our place in a cosmos defined by its cold emptiness is the final chapter of this story. Think about what is required for Earth to be warm. Not warm in the sense of a thermal anomaly embedded in cold space. We have already established that. Warm in the sense of warm enough, warm consistently enough, warm with sufficient stability across sufficient time for the chemistry of living things to operate without interruption for billions of years, because that is what has happened here. Earth has maintained surface temperatures compatible with liquid water, and therefore with life, for more than 4 billion years, not occasionally, not in protected pockets, continuously at a planetary scale for a span of time so long that it swallows most of what the universe has yet done. Yet what is required for that is not a single favorable condition. It is a chain of them, and the chain must hold at every link. Begin with the star. The star, your planet orbits, has to fall within a particular range of mass, not because smaller or larger stars are incapable of warming planets, but because of what their mass means for how long they burn and how they treat the worlds nearby them. A star, significantly more massive than the Sun, burns through its fuel so quickly that the window in which it might warm a nearby world to comfortable temperatures closes before life has meaningful time to establish itself. Stellar evolution does not negotiate timelines. The physics is fixed. Stars above a certain mass are spectacular and prodigiously hot and structurally useless as anchors for living worlds because they are gone too soon, as swelling and dying on timescales that geological and biological complexity simply cannot keep pace with. On the other end, stars significantly smaller than the Sun, the red dwarfs that make up roughly 70% of all stars in the galaxy, present a different problem. Their habitable zones sit so close to the star itself that planets within those zones tend to become tidally locked over time, one face permanently baked in radiation and the other permanently turned toward the dark. Whether life could adapt to that arrangement is a genuinely open question, but the point is that the mass of your star is already, before anything else, a constraint that eliminates most of what the galaxy offers. Suppose the star falls within a suitable range. Now the orbit has to be right. Is it the habitable zone around a sun-like star, the band of orbital distance within which liquid water can exist on a planetary surface, runs from roughly 0.95 to 1.7 times the Earth-Sun distance. That sounds like a generous range, but the actual width of that zone, expressed in miles, is roughly 70 million miles. Set against the distances involved in stellar geography, that number shrinks to something almost implausibly narrow. The nearest star to our Sun sits roughly 4 light-years away, which amounts to something close to 25 trillion miles. The habitable zone your planet must occupy is 70 million miles wide. To feel what that ratio means, if the distance from our Sun to the nearest star were compressed to the length of a standard American football field. Yes, the habitable zone within which Earth had to land would be roughly the width of a single human hair. That is the target. That is the band your planet had to occupy. Not approximately, not for a few centuries while conditions stabilized, but continuously across 4 billion years of orbital mechanics, gravitational tugs from neighboring bodies, and the slow brightening of the Sun as it ages. Earth occupies that zone. The margin for error was, and remains, very thin. But suppose the orbit is right. The orbital distance alone does not determine surface temperature, and this is where the chain reveals a link that is easy to overlook. Without an atmosphere, Earth's average surface temperature would be approximately -18 degrees Celsius. Not cold in an extreme way by the standards of things we have already discussed, but cold enough that liquid water cannot exist at the surface under any sustained conditions. The oceans would be ice. The chemistry that makes living things possible requires liquid water, and liquid water at that temperature is not available. What raises Earth's actual average surface temperature to approximately 15 degrees Celsius above zero is the greenhouse effect, the capacity of certain atmospheric gases to trap outgoing heat and return it to the surface, rather than allowing it to radiate freely into space. That difference, 33 degrees, is not a refinement. It is the entire gift. Remove the atmosphere, and what remains is a frozen rock at the right orbital distance, technically within the habitable zone and completely uninhabitable. The atmosphere is not decoration, it is the mechanism, and the atmosphere has to be maintained. This is where Mars becomes the most instructive object in the solar system. Mars sits at the outer edge of the Sun's habitable zone, and for a period in its early history, it likely had a thicker atmosphere and liquid water on its surface. What it no longer has is a functioning magnetic field. As Mars cooled internally, its core solidified, and the dynamo that generated its magnetic field ceased to operate. Without the magnetic field, the solar wind, the constant stream of charged particles flowing outward from the Sun, was able to strip away the Martian atmosphere over geological time. The atmosphere thinned, the greenhouse effect collapsed, the surface froze. What is left today is a planet with an atmospheric pressure less than 1% of Earth's, as a surface temperature that averages below -60 degrees Celsius, and no liquid water anywhere on its surface. Mars did not lose its warmth because it drifted out of the habitable zone. It lost its warmth because one link in the chain gave way, the magnetic field, and everything that depended on it followed. Earth has maintained its magnetic field because its interior is still active, still generating the heat that keeps the outer core liquid and the dynamo running. That interior activity also drives plate tectonics, which participates in a geological carbon cycle that acts as a long-term temperature regulator, drawing carbon dioxide out of the atmosphere when temperatures rise and releasing it when they fall, and buffering the planet against the kind of runaway warming or cooling that would otherwise be possible over billions of years. Water, delivered in part by icy bodies from the outer solar system during the early history of planetary formation, had to arrive in the right quantities to fill the oceans without overwhelming the land entirely. The Moon, large relative to Earth's size in a way that is not typical for rocky planets, stabilizes Earth's axial tilt over long timescales, preventing the kind of dramatic wobble that would otherwise drive extreme climatic swings. Jupiter, sitting in the outer solar system with its enormous gravitational influence, may have deflected or captured a significant fraction of the debris that might otherwise have bombarded the inner solar system far more frequently than it did. Each of these conditions traces back through a chain of events stretching 13.8 billion years. The mass of the Sun was set at the moment of its formation from a particular cloud of gas and dust. Earth's orbit was shaped by the dynamics of a young solar system full of competing gravitational influences. The atmosphere assembled from the outgassing of a young rocky world. The magnetic field depends on a core that has cooled at a particular rate over billions of years. The water arrived from specific reservoirs during a specific window. None of it was guaranteed. None of it was designed. All of it was required. The warmth you feel is not what happens when a planet orbits near a star. The warmth you feel is what happens when a planet orbits the right kind of star, at the right distance, or with the right atmosphere maintained by the right magnetic field, sustained by the right internal heat, driving the right geological cycles, supplied with the right quantity of water, stabilized by the right moon, partially shielded by the right outer giant. Pull any of those links and the chain does not bend. It breaks. And across a universe that is, as we have established, almost entirely cold, across a galaxy containing hundreds of billions of stars around which planets are now known to be common. The question that follows immediately from all of this is how many of those planets have managed to hold every link in place long enough for warmth to last. The question of how many of those planets have held every link in place is one that astronomers have spent decades trying to answer. And the data from the Kepler Space Telescope, launched in 2009 and trained on a patch of sky containing roughly 150,000 stars, offers what initially sounds like an encouraging reply. When researchers analyzed the transit signals collected over years of observation, a clear statistical pattern emerged. Approximately 1 in 5 Sun-like stars appears to host at least one rocky planet orbiting within the habitable zone, that narrow band of distance where liquid water could in principle persist on a planetary surface. 1 in 5. Not 1 in a million, not 1 in a billion, but 1 in 5. The fraction sounds almost generous by cosmic standards, and when you multiply it through the numbers we have already established, hundreds of billions of stars in the Milky Way alone, hundreds of billions of galaxies in the observable universe, with the latest deep field surveys suggesting something closer to 2 trillion galaxies in total. The resulting count of candidate worlds grows to a number that the mind initially receives as hope. 2 trillion galaxies, each containing something on the order of hundreds of billions of stars, some fraction of which are sun-like in their temperature and mass and age. 1 in 5 of those hosting a rocky world in the right orbital band. When you carry that arithmetic forward, the number of potentially habitable worlds by orbital distance alone climbs into the tens of billions of billions. Written as a figure, it would take more than 20 digits. It is a number so large that it sounds, in the first moment after you hear it, like a reason to believe that warmth is not rare at all, that the universe is populated with warm worlds the way the ocean floor is populated with grains of sand. But orbital distance is only the first filter. It is the coarsest screening, the widest mesh, and almost everything passes through it before the real narrowing begins. A planet in the habitable zone by distance is a planet that receives the right quantity of light from its star. That is all. It says nothing about what that light encounters when it arrives. A world with no atmosphere at all receives that light, reflects some of it, and absorbs the rest, but without a layer of gas to trap energy near the surface. As the heat radiates back into space overnight, and the average surface temperature plunges well below the freezing point of water, regardless of how perfectly positioned the orbit is. We established this already with Earth itself. Strip away the atmosphere, and the average surface temperature drops from 15 degrees Celsius to roughly -18, a difference of 33 degrees, the entire margin between a living world and a frozen one. So the second filter is atmosphere. The planet must have one. It must have the right composition. and it must have managed to hold onto it across geological time without losing it to the same kind of stripping that Mars experienced once its protective magnetic field faded. Which means the third filter is the magnetic field, which depends on a molten outer core, yet which depends on a particular rate of internal cooling sustained across billions of years, which depends on a particular planetary mass, a particular composition, a particular history of formation and impact. And the fourth filter is the geological activity that can regulate atmospheric chemistry over the long run, cycling carbon through rock and ocean and air in a way that buffers temperature rather than allowing it to drift toward extremes. Each filter that gets added reduces the surviving population of candidates, and we do not yet know the transmission rates with any precision. The James Webb Space Telescope is only now beginning to examine exoplanet atmospheres in any detail, studying the light that passes through a planet's atmospheric layers as it crosses in front of its star, is searching for the chemical signatures that might indicate whether conditions at the surface could support liquid water. We are at the earliest stage of that work. The answers are not in hand. But even if we are generous, even if we assume that half of all habitable zone planets retain an atmosphere, and half of those maintain a magnetic field long enough, and half of those sustain the geological cycling needed for long-term temperature stability, the multiplication still produces an enormous number. Generosity piled on generosity still yields tens of billions of warm candidates across the observable universe, and that number still sounds, in the moment you hear it, like comfort. Now, divide by the volume of the observable universe. The observable universe spans a radius of roughly 46.5 billion light-years in every direction, and its total volume comes to approximately 4.2 times 10 to the 80th power cubic meters. That is not a number that yields to ordinary intuition. It is not like saying the volume is very large. It is a number so extreme that even our most inflated estimates of habitable worlds, expressed in their own enormous terms, become statistically invisible when placed against it. A warm world occupies a fraction of a cubic meter if you measure its livable surface layer with any reasonable thickness, even if you generously assigned each habitable world a volume of many trillions of cubic meters to account for everything above and below its temperate surface. And even if there were tens of billions of such worlds, the ratio of warm volume to total volume would require scientific notation to express, with a negative exponent large enough that it would not look out of place in a discussion of quantum mechanics, rather than geography. The warm fraction of the observable universe is not small in the way that a needle in a haystack is small. A needle in a haystack is visible if you look closely enough. The warm fraction of the universe requires a form of mathematical notation specifically designed for quantities too small to write in any ordinary way. What the Kepler estimate gives is a numerator, a real one, a significant one, a numerator that suggests warmth is not a singular accident confined to one pale world in one unremarkable galaxy, but the denominator is the observable universe itself, and the observable universe does not negotiate. Even the sun's gift of warmth comes with an expiration date printed in the physics of stellar evolution. Even the sun's gift of warmth comes with an expiration date printed in the physics of stellar evolution, and that expiration date is not unique to our star. It applies to every star burning in every galaxy across the observable universe, and when you hold all of them together, all 200 billion stars in the Milky Way, all the hundreds of billions of galaxies, all the uncountable fires spread across 46.5 billion light-years of observable space, what you are actually holding is not a permanent condition. You are holding a phase, a temporary arrangement of matter that the universe passed through, is passing through now, and will eventually leave behind as completely as a river leaves behind a stone it has long since flowed past. The era of stars did not begin at the beginning, and it will not last until the end. What physicists call the stelliferous era, the age of starlight, the period during which the universe actively produces and sustains burning suns, spans a total duration of roughly 100 trillion years. That number sounds enormous, and measured against anything from ordinary human experience, it is. But it has a boundary on both sides, and the boundary that faces the future is not as distant as it first appears, because we are not at the beginning of this era. We are well into it, as star formation in the Milky Way today proceeds at a rate of roughly 3 solar masses of new stellar material per year, 3 suns worth of gas and dust collapsing into new fires annually across a galaxy that contains between 200 and 400 billion stars already burning. 3 solar masses per year. In a galaxy of that scale, that rate is not a flourishing. It is a decline. The peak of star formation across the universe occurred roughly 10 billion years ago. At that earlier time, galaxies were forming new stars at rates tens of times higher than anything we observe today. The universe was younger. The gas reservoirs were fuller. The raw material had not yet been locked inside existing stars or ejected into the space between galaxies by stellar winds and supernova shockwaves. The forge was running at full capacity, and now it runs at a fraction of that pace, and the fraction shrinks with each passing era. What we observe today when we look up at the night sky, that dense scattering of light across the darkness, is not the universe at its most luminous. It is the universe in a long, slow decline from a peak it passed billions of years before the Earth existed. But the decline will not be rapid, and this is the part that gives the stelliferous era its strange character. Because red dwarfs, the smallest and dimmest stars, burn so slowly and so efficiently that they will continue shining long after every sun-like star and every giant blue star has exhausted its fuel and gone dark. Red dwarfs burn at surface temperatures only a fraction of the sun's, effusing hydrogen so conservatively that a single red dwarf can sustain itself for 10 to 15 trillion years. Not billion, trillion. And because they compose roughly 70% of all stars in the Milky Way, and because not one of them has yet had time to die in the 13.8 billion years the universe has existed, they represent the last, longest chapter of the age of stars. When the last red dwarf finally exhausts its hydrogen and contracts into a cold, inert remnant, the stelliferous era ends. No new stars ignite. The raw material has been used, scattered, or locked away in forms that gravity can no longer compress into fusion. The forge does not merely slow, it stops. What follows is not nothing, but it is colder and stranger and longer than anything that came before. The objects that remain, white dwarfs, neutron stars, black holes, carry the memory of the stellar era in their structure, but they no longer produce light and heat through the same mechanism that made the stars burn. White dwarfs, the cooling embers left behind when stars like the sun exhaust their fuel and shed their outer layers, begin their existence glowing with residual heat, but there is no ongoing fusion inside them to replenish what they radiate away. They cool, slowly, over timescales that dwarf even the stelliferous era itself. They release their stored heat into the surrounding darkness and dim toward temperatures indistinguishable from the background of space. Now, the cooling time for a white dwarf to fade entirely from any meaningful warmth extends over quadrillions of years, numbers so far beyond the current age of the universe, that the universe's entire history so far would need to be repeated millions of times over just to reach them. And at the end of that process, what remains is sometimes called a black dwarf, a cold, dark, crystallized sphere of compressed matter drifting silently through a universe that no longer lights it from any direction. Black holes endure longer still. A stellar mass black hole, the kind left behind when a massive star collapses at the end of its life, will evaporate through a process described by the physicist Stephen Hawking, a slow quantum leaking of energy from the event horizon, over a timescale of approximately 10 to the 67th power years. Written out in full, that number would require 67 digits. The current age of the universe requires 10 digits. The evaporation of a single stellar mass black hole outlasts the current age of the universe by a margin so extreme that our entire cosmic history so far is, relative to it, essentially the first instant of the first moment of the first day. And the supermassive black holes that anchor the centers of galaxies, objects containing millions or billions of solar masses, will take even longer, with evaporation timescales reaching 10 to the 100th power years. 10 to the 100th. Mathematicians have a name for that number: a googol. A supermassive black hole will take a googol of years to finish evaporating, and when it finally does, what replaces it is a diffuse spread of low-energy particles expanding outward into a universe that is by then unimaginably dark, unimaginably cold, and unimaginably empty. This is the long arc. Warmth has a beginning, and it has an end, and the end is not a sudden catastrophe. It is a gradual dimming, a cooling that proceeds through phases of decreasing intensity across time scales that compound upon each other until the numbers themselves stop feeling like time and start feeling like geometry. But there is a compression that brings it into sharper focus. If you were to map the entire future history of the universe, from now through the last red dwarf, through the cooling of the last white dwarf, through the evaporation of the last black hole, onto a single calendar year, the question you would need to ask is where, on that year, the age of starlight sits. The stelliferous era, all 100 trillion years of it, would occupy only the briefest opening fraction of that year, a window of cosmic time so narrow relative to what follows, and that the entire era of stars is less than a rounding error in the total duration of the universe's history. And within that narrow window, the current moment sits near the middle of a decline that has been running for billions of years already. Warmth, then, is not only rare in space, it is rare in time as well, concentrated into a phase that has already passed its peak, that will persist through the slow burning of the last red dwarfs and then yield entirely to the long, dark, cold arithmetic of the degenerate era and the evaporating era that follow. Every star you can see in the sky tonight is evidence of that phase still continuing. In and but the question of what fraction of cosmic time that phase occupies, what portion of everything that has happened and everything that will happen is illuminated by starlight, is a question whose answer sits just at the edge of what this reckoning has so far considered. And the question of what fraction of cosmic time the stelliferous era occupies, that narrow window of starlight between the cold before and the cold after, has an answer that requires the kind of compression that initially seems like an exaggeration until you follow the arithmetic and find that it is simply what the numbers produce. Take a single calendar year, 365 days, from midnight on the 1st of January to the last second of the 31st of December. And now map onto that year the entire future history of the universe, not from the Big Bang, but from right now, forward through everything that will ever happen. The last stars burning down, the white dwarfs cooling, the black holes slowly evaporating over time scales reaching a googol of years. Place all of that on this single year, and now ask where the stelliferous era, all 100 trillion years of it, every star that has ever burned or will ever burn, sits on that calendar. The answer is that it sits at the very beginning of January 1st, not the morning of January 1st, not the first hour, the first fraction of a millionth of a second after midnight. The entire era of starlight, all 100 trillion years of it, fits inside a sliver of time so narrow that no clock ever built could measure it, compressed to less than a blink at the opening instant of a year-long darkness. Let that image settle. The entire era of starlight, every sun that has ever burned, every world it has ever warmed, occupies less than a blink at the start of a year-long darkness. And then the year continues. January passes, February, spring comes and goes, summer, autumn, the long turn toward winter again. And in all of those months, there is nothing to see, nothing to feel, no warmth anywhere, only the slow arithmetic of cooling matter and the universe drifting deeper toward 2.7 Kelvin, and then below 2.7 Kelvin, as even that residual warmth of the cosmic microwave background continues to thin and cool with the ongoing expansion. Nearly all of the time that will ever exist in this universe passes in that long, dark, cold arithmetic after the blink. Stars were not the dominant feature of cosmic history. They were a brief overture before a silence that dwarfs them by a margin that the calendar comparison captures, but still cannot quite make feel real. The darkness after is not a footnote. The starlight is. But even within that opening fraction of a second on January 1st, even within the era of stars, which is itself nearly negligible in the full sweep of time, there is a deadline that sits far closer than the 100 trillion years might suggest. The Sun has approximately 5 billion years of hydrogen burning remaining, and 5 billion years sounds, at first, like a number safely beyond concern. It sounds like the kind of number that excuses you from thinking about it. And the Sun has already burned for roughly 4.5 billion years, and the Earth has carried liquid water and life for most of that time. So 5 billion more years feels like a reasonable inheritance, a generous extension, more time than anything could possibly need. But that confident accounting contains a complication that most descriptions of the Sun's lifespan quietly omit. The Sun does not burn at a constant rate. It grows gradually brighter as it ages, a consequence of the slow accumulation of helium in its core, which increases the pressure and temperature required to sustain fusion, which in turn causes the outer layers to radiate slightly more energy over time. This brightening is not dramatic on any human timescale. In a million years, the difference is negligible, but on the scale of a billion years, the increase becomes approximately 10%. 10% more solar energy arriving at the Earth's surface than arrives today, and 10% sounds small. 10% more warmth sounds almost pleasant, the way a slightly warmer afternoon sounds pleasant. But the Earth is not a body that absorbs extra energy and shrugs. The Earth has a climate system that is, on geological timescales, sensitive to even fractional changes in the energy it receives, and 10% more incoming solar radiation is not a small perturbation to that system. It is enough to push the climate across a threshold, a point at which water vapor, itself a greenhouse gas, begins to accumulate in the upper atmosphere faster than it is lost to space, amplifying the warming further, trapping more heat, driving more evaporation, trapping still more heat, and in a feedback loop that does not find a new equilibrium, it simply accelerates. The oceans begin to evaporate, not slowly and partially, the way a lake might shrink in drought, fully, systematically. Over geological time, the Earth's oceans would vaporize into the atmosphere, and the surface temperature would rise to levels where liquid water could not exist anywhere on the planet. The world that has held liquid water for more than 4 billion years, the world whose entire biological history is inseparable from the presence of that water, would become a dry, hot, uninhabitable surface under an atmosphere heavy with steam and carbon dioxide. This is expected to occur in approximately 1 billion years, not 5 billion, 1 billion. The Sun's remaining hydrogen burning time extends to 5 billion years, but the window for a habitable Earth closes roughly 4 billion years earlier than the Sun itself runs out of fuel. In a single observation, the familiar narrative of the Sun's lifespan, which already felt enormous, contracts by 4 billion years. The deadline did not move gradually. It moved in one sentence. So consider where that leaves the reckoning. Warmth is vanishingly rare in space. confined to a fraction of cosmic volume so small that expressing it as a number requires negative exponents with dozens of zeros, and nearly all of the time that will ever exist passes in darkness, at temperatures near or below 2.7 Kelvin, in a universe that has finished burning and is cooling toward a final equilibrium that no process will ever reverse. The stelliferous era is a fraction of a millionth of a second on a year-long calendar, and within that fraction, the Earth's window of habitability, the specific warmth that allows water and life and everything that has ever thought or felt or looked upward, is narrower still, already more than 4 billion years spent, perhaps 1 billion years remaining before the warmth that sustains life becomes the heat that ends it. This is not a coincidence or an oversight in the design of things. It is what the second law of thermodynamics, applied at cosmic scale, produces. The universe moves in one direction, from concentrated energy toward diffuse equilibrium, from hot toward cold, from ordered toward disordered, always and without exception. Every star is a local and temporary resistance to that direction, a place where gravity compressed matter densely enough to ignite nuclear fusion and push back, briefly, against the spreading cold. But the resistance is temporary by definition. The fuel is finite. The expansion continues. The universe is not oscillating between warmth and cold the way seasons alternate. It is moving, without reversal, toward 2.7 Kelvin and beyond, and nearly all of the time that will ever exist finds it there, cold, dark, and still. The warmth is not the baseline occasionally interrupted. The cold is the baseline, and the warmth was the interruption, and the interruption is already most of the way through its duration. And if you gather all of that, the spatial rarity of warmth, at the brevity of the stellar era against the full span of time, the narrowing of Earth's habitable window before the sun even begins to die, and hold it together in your mind as a single picture, something else becomes visible, something that sits underneath all the individual numbers and extends through all of them at once. It is not a new fact so much as a structure that was always there, governing every fact you have encountered in this entire account. It is the reason the numbers point in the direction they point, and the reason they could not point in any other direction. The second law of thermodynamics states that energy, left to its own devices, moves from regions of higher concentration to regions of lower concentration. Heat flows from hot to cold. Order tends toward disorder. Concentrated energy tends to spread out, diffuse, and distribute itself evenly across whatever space is available. This is not a temporary tendency or a statistical preference that might occasionally reverse. It is the most reliably observed principle in all of physics, operating without exception across every scale from the submicroscopic to the cosmological. A hot cup of coffee left on a table does not spontaneously become hotter. It cools. The room does not contract its warmth back into the cup. The warmth spreads into the room, and the cup moves toward equilibrium with its surroundings. And this is precisely what the universe is doing, at every scale, in every region, across every moment of its existence. Stars are local exceptions to this spreading. They are places where gravity compressed matter so densely, over such long periods of time, that nuclei began fusing, and energy began radiating outward. In that sense, a star is a resistance, a temporary structure that locally maintains a concentration of energy far above the surrounding average. But the word that governs that sentence is temporary. A star radiates because it is losing energy. Every photon that leaves the surface of a star and travels outward into the dark is energy leaving a concentrated region and spreading into diffuse space. The star is not building towards something. It is spending itself. The light that crosses 8 minutes of space to warm the surface of the Earth is energy that the sun will never have again, spread now across a sphere of space with a radius of 8 light minutes and growing every second. The warmth arrives here, but the sun is, in the most precise physical sense, cooling down. They're not quickly enough for any human instrument to easily measure against the ongoing fusion, but the direction is fixed. Every joule of energy radiated is energy that has moved from concentrated to diffuse, from ordered to spread, from useful to equilibrium. The second law does not pause for starlight, and this means something about the relationship between warmth and cold that is deeper than the simple observation that cold dominates by volume and duration. It means that warmth is not merely coexisting alongside cold in a stable arrangement where each holds its territory. It means that warmth is actively producing cold, that the very process which generates heat locally is by the act of radiating that heat outward, contributing to the eventual diffusion of all concentrated energy into the vast, dark, and near-empty space that makes up the overwhelming proportion of what exists. Every star that shines is hastening the universe toward its final thermal state. The very process that creates warmth locally contributes to the ultimate triumph of cold universally. The campfire does not hold back the night. Every log that burns is converting fuel that could have remained unconverted into heat that disperses into the surrounding darkness, and the darkness absorbs it without changing character, without warming in any way that persists, without accumulating warmth the way a battery accumulates charge. The universe does not need to fight warmth. It merely needs to wait. This is what makes the thermodynamic argument different from the spatial and temporal arguments. As though the spatial argument showed you that warmth is confined to a negligible fraction of all that exists, the temporal argument showed you that warmth is confined to a negligible fraction of all the time that will ever pass. But the thermodynamic argument shows you that these two facts are not accidental. They are required. The laws of physics do not permit any other outcome. Cold is not a condition that warmth might eventually overcome if the right circumstances arose. Cold is the direction. The universe began in an extreme state of concentrated energy, and every process that has occurred since, every fusion reaction, every stellar emission, every photon crossing the void, every moment of biological warmth generated by a living body metabolizing its food, has moved energy along the path from concentrated to diffuse, from available to spent, and from hot toward the final equilibrium. The end state is cold because the beginning state was hot, and the second law has been the governing rule of every step between them. We have moved through this account in stages. First, the simple intuition that space is merely cold in the way a winter night is cold was taken apart, and the actual number, 2.7 Kelvin, a temperature no laboratory on Earth had achieved before the mid-20th century, was placed in front of you in full. Then we traced where that cold came from, all the way back to the cooling of a universe that was once unimaginably hot, and we watched the expansion carry temperatures down over nearly 14 billion years to arrive at the number that satellites now measure to 4 decimal places. Then we surveyed the hot exceptions, the stars and their cores, the supernovae, the accretion disks, the planets warmed by the right distance from the right kind of star, and counted what fraction of space and time they occupy. And then we watched even those exceptions begin to fail, as star formation declined from its peak, as Earth's own window began to close, as the long cooling of the degenerate era stretched out across timescales that make the stellar era look like a brief morning. Each stage revealed a deeper layer of the same structure, and now the structure itself is visible. The cold does not surround us the way darkness surrounds a campfire, contained at a distance, while the light holds its ground at the center. The cold is the night. The campfire exists within it, briefly, and when the fire goes out, the night does not need to rush in, because the night was already everywhere. So the terrifying truth is not the number 2.7 Kelvin. The terrifying truth is the proportion. Warmth exists in an almost immeasurably small fraction of all that is, for an almost immeasurably brief fraction of all time. And it exists there not by holding the cold at bay, but by burning through the very fuel that temporarily permits it to exist at all. What you have been given, across all the distance this account has traveled, is a single coherent picture, not a collection of alarming facts, not a sequence of unsettling comparisons, but one picture, and standing at the end of it, you can see the whole thing at once. The universe is, in its default and overwhelming condition, cold. Not cold the way a winter morning is cold. Not cold the way the upper atmosphere is cold, but cold in the way that 2.7 Kelvin across billions of light years of void is cold. A temperature that spans the largest structures ever mapped, that fills the spaces between every galaxy cluster, that existed before any star ignited and will persist long after the last one fades, that represents not an accident of local circumstance, but the thermodynamic destiny of all energy that has ever existed or will ever exist. And here, in the middle of that, is Earth, a planet that has maintained liquid water on its surface for more than 4 billion years. A planet where, for all that time, warmth has not merely visited but persisted, where the energy arriving from a nearby star has been caught, retained, cycled through weather systems and oceans and the metabolisms of living things, are passed from organism to organism across an unbroken chain of biological inheritance that stretches back to chemistry in warm water, forward to every cell in your body generating heat right now. 4 billion years is a span so long that the mind cannot hold it honestly. If you compressed the entire current age of the universe, 13.8 billion years, into a single calendar year, Earth's continuous record of warmth and life would occupy roughly the final 3.5 months of that year. Not a moment, not a flash, a genuine era, sustained and stubborn and real, but set against the cold that surrounds it in every direction, and against the cold that will eventually reclaim it. That era is precisely what it feels like when you say it aloud. Something that happened here, for a while, yet against all the odds that space and time and thermodynamics arranged against it. This is not a reason for despair. It is a reason for attention. Because the alternative to understanding this, the alternative to holding the full picture clearly, is to move through the warmth without noticing it, to treat the temperature of the room you are sitting in as background, as default, as the unremarkable starting condition of an ordinary moment. And it is not. The warmth in the room you are sitting in is a local rebellion against the cosmic default, sustained by a star that has been burning hydrogen into helium for 4.5 billion years, received by a planet tilted and positioned and atmospherically wrapped in a configuration so specific that a fractional change in any one parameter closes the window. As that warmth arrived here across 93 million miles of vacuum in 8 minutes, and the planet held on to it, and the life on this planet learned to run on it, and you are the current expression of an unbroken 4 billion year argument against the cold. Every breath you take is powered by molecular processes that exist because warmth persisted here long enough for complexity to accumulate. Every thought you are having right now is the product of a nervous system that operates within a narrow thermal band that the universe works, over time and at every scale, to eliminate. None of that was guaranteed. None of it was written into the structure of things as a permanent feature. It arrived the way all warmth arrives, by conversion of something finite, by the spending of fuel that does not replenish, by the temporary concentration of energy in a region that the second law will eventually smooth back into equilibrium. The cold does not need to rush. It has the entire future of a cooling universe to complete its work, and the work is already well underway. But it has not finished here. The sun is still burning. The atmosphere is still holding. The oceans are still liquid. The chain of warmth that started 4 billion years ago on this particular world, in this particular corner of a galaxy that is itself a brief bright feature in a universe that is nearly all dark and cold and empty, is still unbroken. The universe is cold, nearly all of it, nearly all of the time, but not here, not yet.